To talk about the use of AI in medicine, especially medical images, we'll start from the segmentation task. You probably heard it mentioned, but actually, if you're trying to pinpoint exactly what's segmentation, you can see that there are multiple different tasks. So basically, it's you want to say there's something. But let's see what we might mean by recognition. In this part of the example, I will use mostly natural images more than instead of medical images. So you have lots of things. So one could be verification. Is that thing here that I'm pointing to a lamp? Or you might ask the software, where are the people? You might ask, is this building one specific building? And or you could ask what objects are present, lots of them, or you could do a categorization where this is an outdoor image of a city. And you could also do an activity event recognition. So that's mean, I don't know, like the Sunday stroll or whatever. So these are all related but different tasks. And let's see what are the intrinsic difficulties in doing these tasks with images. So suppose that I tell you to write an algorithm that recognizes a bike. A bike, according to the competitive cycling organization, is one made by two triangles. Actually, in races, you can use bikes only with these specific geometries, with two triangles and two wheels. So you can, these are, by the way, pretty distinctive shapes, much more clear than, I don't know, the shape of a face. So you might say, okay, I look for an image with two circles and two rectangles. It shouldn't be that hard to implement, but you can always immediately see that's extremely obvious to us that there is a bike in these two images, but we don't see any triangle and any circular structure. We also get to this very different kind of question, is like asking ourselves, is this one a bike? And the answer, by the way, is dependent on your task, because this probably is a road sign. So if you are building an autonomous driving system, that's a sign representing a bike. That's not the object bicycle, but it's representing the bike. Now, let's try to think, is it really so hard, and in case why? Suppose that you have this image of a chair, and you are asked to find the chair in the image, that's this actual chair. You can take this patch, scan the image, compute a correlation, and you can find not really too high correlation except when the two overlap, and you might say, okay, I can do that. But if I ask you to do in the same way, find the chairs in these images, the idea of matching a template is you can throw it out of the window immediately. Because, of course, doing this kind of correlation points to all kinds of random places. Because if we go back to the 70s, they said that a popular method is that of template matching. There are/were lots of algorithms to detect extreme points, which are corners, which generally define pretty well the salient point of an image, and you can correlate all of that point with that of a template. But these are inadequate for three-dimensional scenes for a number of reasons, like occlusion, changes in viewing angles, and the articulation of parts. So one of these algorithms that was based on extracting a number of salient points. It worked very, very well for instances Like when you have very distinctive images, such as when you need to pick up a logo in a picture, but it's not good at all for categories because all of these are chairs, but by knowing the position of the corners, you can't do much about it. Of course, it can get much higher. This, of course, is well chosen, but if you try to spot this mimetical animal here, which is around here, it's extremely harder. There are lots of applications to recognize objects in images. Nowadays, you have automatic shutter-free photography. You don't need to click. They just recognize when you're smiling and it shows the image. Autonomous driving works relatively well. And in robotics, it's even harder because picking objects is really, really hard. And there are some, of course, that's what the point of this talk, recognizing medical imaging. In this case, they use the example of skin lesions. And to categorize them, you need to look at a pretty convoluted series of features like the shades, if you have different colors in sequences, and so on. And that's what we're doing. Now, why is this hard? Because there's a lot of intrinsic variability, camera position, illumination, shape of the objects that you're looking at, etc., etc. Now, how many object categories are there? It's, of course, the concept of category is pretty dependent and elastic if you want, but approximately cognitive psychology studies tell us that a kid by the age of 6 can recognize 10K, 30K categories. And when I first was reading the textbook about this, I was saying these are way too many, especially for a kid 6 years old, but turns out that it's true. You might need to remember that categories can intersect. So you don't have just dog, but you have pet, animal, small dog, purebred dog, happy dogs. These are all sitting dog. So these are kind of categories, and so you get pretty easily to this kind of numbers. And our brain is extremely fast in doing this kind of categorization. It learns it. I don't know if you could say fast because it takes years. So when we say a kid 3 years old already knows how to do that, it still took 3 years. So it's fast compared to the human lifespan, but whatever. So one of the challenges is the variable viewpoint. That's typical of natural images. You don't have any preferred direction to take a picture of a statue, because even in a statue you can have a person lying down, standing up, and so on. And by the way, your brain, even if you are looking at something completely distorted because you are from the side, looking from an upper floor, it automatically corrects the perspective. And even in medical imaging, many findings don't have any preferred direction or location. If you have a tumor in a CT, it can be in the apex of the lung, in the middle of the lung, and the position might be either irrelevant or relevant to the pathology, and it's hard to describe it like when you're looking at a CT image, saying from a computer science point of view, this is in the third lobe of the lung. It's not really that easy to point down. We will see that in the brain there is a way to standardize coordinates with old school algorithms, but in other organs it's completely impossible, let alone in microscopy. In natural images, there's the challenge of variable illumination. There's the challenge of scale. That's, I don't know if you remember this Apple commercial. This is an actual scale. That's one of the smallest actor and the highest human on Earth. There's the challenge of deformation. Of course, we picked the most flexible humans out there, but still we have lots of different positions. We have the challenge of occlusion. This probably there's a part of painting. This is probably not really natural. There are some artifacts, but still, and in X-rays, in planar X-rays, this is really typical because you have really an overcrowded environment. Or also like this kind of images here. There's the challenge of background clutter. The background might be full of stuff, and if you choose well, it might be the most confounding you can imagine, or like this. And this probably is even, let me say, intentional, like probably this bird evolved to match the color of the branches it standing on. And that's the challenge of intra-class variation. So we need to recognize a chair, but when we're talking about radiology, when we're talking about even like lung tumor, it can be for one kind of lung tumor, so small dots, very small 1 centimeter circles. For other variants, it can be a low-grade inflammation that takes a quarter of a lobe. And so it's pretty, you have a really huge number of challenges if you want to define from the bottom up how to recognize findings in an image. Let's do a super quick history of image recognition, what worked before deep learning. In 2011, we had optical character recognition that worked pretty well, recognizing numbers and letters. Face detection, which means detecting where a face is or if a face is present. And instance level recognition, like you have this logo and you want to recognize that specific logo is present. And finally, the detection of pedestrians, kind of. And mostly that was about it, which kind of image recognition was possible before deep learning. Now, what we can do nowadays, we have robust image classification across thousands of categories at the level of human capabilities, and I will say most likely even higher. Face recognition at scale, at extremely high potential, even too high, probably. And we also have image synthesis. Probably these slides are 2 years old, and we are doing much better than this, and this was okay. And sorry, this was not okay, these were amazing. So that paper, I think it was 2021 from NVIDIA. So these are all, these people do not exist. I guess that paper was probably not the paper, but the commercial launch was called that way. It was called, these people are not real. And you even had, these are all generated from AI. And you could, with some sliders, change the features. So you could say, long hair, short hair, and you drag the slider and change the appearance. And same for skin color and so on. And you could control it. Nowadays, of course, you know, we have Dolly, we have Sora that can generate images from a text prompt and even videos from a text prompt. And they are, of course, pretty good at it. Now, what are the things that matter here in recognition? The choice of the classifier method, the deep learning feature. the deep learned features and the data, where we used to say that more is always better as long as it was good. We will see in the next lecture how we can you go to the next level by doing away with labels, because there's only a certain level of accuracy that you can get on labels and a certain amount of labels that you can get. Indeed, we are seeing more powerful models trained for noisy labels. Now, here's a brief history of the datasets that were present. In 2005, there was the Pascal video database, which had 20 categories of objects with their bounding boxes within an image. Then there was the famous CIFAR10, probably used that in some intro to deep learning. It was 60,000 32 by 32 images in 10 classes. So you had 6,000 examples of each number in an unprinted function. The ImageNet competition about it's made of iconic objects, typical of categories, that nowadays it contains, I guess, 1,000 categories. And then we go all the way to the Lion database, which contains 6 billion noisy image text pairs. So there was this kind of challenges. 12 with 20 categories, classification, you wanted to know if there was X in the image, detection, draw a box around the X, and segmentation, which class is in each pixel. So you could do these 3 kinds of tasks. The ImageNet went from the first setup to 20 object classes and 22,000 images to 1.5 million images and 1,000 object classes. And you could see that there are huge varieties of object classes you can say the different kinds of categories, like bottle can be a pill bottle, a beer bottle, a wine bottle, water bottle, and so on. You can see how we get to 20K categories, like car and race car, wagon, minivan, jeep, cab, and so on and so on. There's a huge, let's take a look at the kind of features that you get, the kind of things that you need to deal with. So you have the amount of textures that can go from completely irrelevant to extremely important. The importance of the color. Coffee mug can be any color. For a bagel, the color is probably relevant, is a kind of relevant. For red wine, of course, is fundamental. The importance of the shape. For a puzzle, is not important. For a bell, that's everything. And the sides can be, well, that's kind of variation. You go for all sizes, from oranges to airliners. So let's recap the image classification. You have, what you do is that you have an input image, and as an output, you output the label for the whole image, assuming there's only one object inside. But let's see the definition of the different kinds of recognition tasks that we can do. We have instance recognition, where we recognize where objects are in a cluttered scene. That's an old kind of task. Well, it's still relevant today, but this is an old example. You get, you want to find this and this within this image. And that used to be popular for even 15 years ago on cars. You could get traffic sign detection reliably enough. But the shapes and everything were pretty distinctive. Image classification is describe what the image is showing. Then we have the task of semantic segmentation, which means assigning every single pixel to a class. That's opposed to instance recognition, where because here the contouring follows the edge, while before you just drew a bounding box. We have instance segmentation, where instead we want to delineate every separate object. So you want to, like, you can see where it can be pretty relevant. If you want to recognize the cars, most likely you don't want 0 and 1 with 1 for a car, but you want to recognize every single car to make a model of the world. There's also panoptic segmentation, where you get semantic and distance segmentation together. Here's a brief kind of table of all the possible tasks that are done within the realm of image recognition. And you can see that it also changes the level of granularity. Like this kind of task for medical image analysis could be, you give a whole slide of a microscopy exam and tell, is there a tumor or not? Is it healthy or not? Object detection, bounding boxes, can be where is the anomalous region. Then you want to search for, you might want to do instance recognition, semantic segmentation. It can have lots of applications, not only spot the malicious part in the image, but even you have to do an operation planning, and it's delineate all the bones, all the contour of the organs, and so on. And you can see that there are lots of options. So let's go to see how AI enters into that. Just a quick recap of what AI is. You've probably seen it, hundreds of small variations of this slide. So AI is a very general concept of advanced algorithms, whatever that means, mimicking human reasoning. Machine learning is much better specified. It's advanced statistical techniques for classification and pattern recognition on data that are characterized by having a very high dimensionality. And deep learning is the ensemble of techniques based on deep neural network. Now, very quick history. Neural networks are all the way from the 60s. Support vector machine are from the 80s. Speech recognition was already 30 years ago. We had chess playing in 96 and automatic translation with moderate success in 95. You have probably seen multiple variations of that previous graph. Deep learning can be seen not just as the smallest ensemble, but by the intersection between machine learning and AI, where in this case here you define AI as a system that is intelligent using rules, while machine learning is in this model is a self-learning algorithms that learns model from the data. This is a possible definition of data science, where you integrate AI and big data together. So the core of that is the concept of learning. This goes to the concept that was introduced in this paper in 2009 about the unreasonable effectiveness of data, because, well, I come from physics, I'm a physicist, and what usually a physicist want to do is go get the simplest model with the least amount of free parameters, or like one free parameter at most, derived from general rules and explained by elegant mathematics, and that's the basic of physics, chemistry, and so on. However, lots of things in the world cannot be explained in this way. If you talk to a physicist, probably they say, here you need, for psychologists, economics, and so on, you need to use chaos mathematics, complex system mathematics. Here what enters is the data approach, which allowed, experimentally we see it every day, great advances in several fields. And indeed, in this example, it was said that for many tasks, once you have 1 billion or so example, we have the full set of that approximate everything that we might need. And these can be applied pretty well to our world, to what we want to do. Now, what's the concept of learning? We don't have, the thing about learning is that we don't have the model. We have the data. We have a learner that, after the training phase, gives in output a model. And then we can move to the inference phase where we get some new data, some inference data. We apply the model that was learned from general principles from the data, and we get our own output. In the case of deep learning, that's achieved with neural networks, because you've probably seen that given that you have nonlinearities, that you have some hidden layers, it was proven that a network can approximate any existing function in the world. So the concept is that this basis of function, which is implied by deep learning, can learn any single existing function. So if it exists, it can be found. So what we want to do is basically look for a needle in an haystack. We have the space of all functions that exist in the world. We have whether we might realize it or not, that's important, a space where we are searching, and we have a solution somewhere here, which is the needle in our haystack. With a deep neural network, if it's deep enough, you really cover almost all of the space, by the way, making the search even more complicated. However, we can make some hypotheses and use much smaller searches of space. So suppose that we want to fit a polynomial function or a linear function. We search only along this very small part of the space, and if the true solution is according to this model, that's good for us. But if it's not, we will never be able to find it. So let's apply learning to vision. We have some problems that we open up. So how do we represent the input and the output? What's the objective? In learning, we get a model by optimizing some kind of objective function. And how we define the objective? What is the space of the hypothesis, and how do we optimize? And finally, what data do you train on? If we want to apply that to the case of image classification, we have the issues of how, again, we have the same 2 points, and we need to assume that the hypothesis space is really able to express all the kinds of issues that we have. We need to assume that we can actually search along all of this space. That's not a given at all. And we also need to assume that we are training on the data that we care about, and that's the so-called issue of posterior shift, that it's not that trivial at all. So in this kind of visualization, we have here all of the space. Here we have in white the function that we are trying on. We have all of the functions that fit well, and here we have maybe some prior hypotheses on where our solution will be. And we can see that if our prior assumptions are good enough, we will be constrain a bit our solution to get closer to the true one. That, of course, doesn't often work well. In this case, it's a colorization experiment. Here, the authors tried to train the network to give colors to all of these images, but then when they put it on, they actually did this, they put it on Reddit, asked the user to upload their images, and they all got some kind of sepia-looking brown images that were not really colorized very. You can see here the network was using the full gamut of colors, and here it was just doing some very minor colorization. Okay, so the concept of overfitting and things like that, it's you've seen it pretty well, so we can go pretty fast. Suppose that is our training data. If we train with a polynomial, a degree 1, it's underfitting. If we train with a degree 2, it's fitting better. And if we go to the higher degrees, the more degrees that we add, the worse it starts to get. We get a function that passes perfectly along all the examples, but does not generalize. So in this case, when we have two separate data sets for training and validation, and in underfitting you have a very high error on both data sets. With the appropriate model you have the lowest error, and with overfitting you have the highest error on the test set. Okay, let's see what, however, when we go to a very high dimensional space, if I asked you what does the symbol does, you could fit this and get to this kind of relation. Or you could also do this very stupid kind of model that perfectly fits the data. That's model, it's called the filing cabinet. You take every example that you see, you put it in your list of examples, and if you find another point that is the same for as an input that you've already seen, you will return what you have seen previously, otherwise you return 0. And of course, if you ask yourself what the approximation error be and the generalization error be, that will be pretty high. This kind of model you will get to work this way. We need to it's pretty easy to see the difference between generalization and memorization in this example, because the X range here is pretty well defined. When you go to the very high dimensional space, that's not as well defined anymore. Okay. So, to summarize, to fit well, if you are underfitting, you can add more parameters, more features, more layers, whatever. If you are overfitting, you have two options, either remove parameters or add regularizer. And basically, you are selecting a hypothesis space of function with just the right capacity. Let's remember regularization. You've probably, in some statistic courses, saw the ridge regression and the lasso regression. I hope so. What you do is, instead of fitting the data fidelity function, which probably could be the sum of squares in the most trivial cases, you also minimize a function with some kind of weight lambda. You also minimize a function of the parameters you're learning themselves. One very effective way to do that in theory, in practice it has a lot of issues, is just to penalize the value of the parameters that you are estimating. Because the idea behind that is that then every parameter that will not be useful will be put to 0 during the fit. And that's the case of ridge regression and Tikhonov regularization. Therefore, you can play with 3 tools in search for the truth: data priors and hypotheses. Data priors and hypotheses. So you have the space that can be found by your network. The deeper your model is, the more function that you can look for. Data, the more data that you had, the better the fit. The stronger the constraint, and that's your prior that can hopefully work in some kind of orthogonal direction. Let's see on a one-dimensional fit, see the effect of that. Let's say that we have only 1 point. Let's see what happens when we have more points. And like in this case, we need to fit theta 0 x plus theta 1 sine of x with only 1 point. All of these functions, all of this combination of theta 0 and theta 1 have exactly the same fidelity values, while the more points we add and the farther up they are, the more you constrain all of them. And indeed, you can see that the two converge. In this kind of other experiment, when we are fitting a quadratic function, we can see again that the more points we add, especially over a larger range, the more constrained is our fit. Now, let's see the effect of using priors. Suppose that here you add a constraint where you want to minimize the norm of these both parameters. And in this case, even with just 1 point, we can see that we get a more decent fit because it's pushing, with a constraint written this way, both parameters to be close to 0. And so the combination of solutions where both are very high or both are very low doesn't work. But of course, if our regularization gets much higher, our fit will be 0. So we need to strike a balance, and there's no theoretical way to know what's the optimal value. And then we see that's extremely trivial in the case of polynomial fit. What happens if we change the fitting function? I'm using a square, I'm fitting 2 points, my results will be a parabola. I'm fitting with a line, my results will be a line. I'm fitting with y equals 0, and I get a straight line. Or even if I fitted with y equal theta 0, I will fit the mean, but I will not be able to predict any kind of variation. So, concluding remarks about this part is that learning turns data, you go from data to an algorithm. And this is a major component of modern computer vision. The goal of learning is to extract lessons from past data. And however, unless the future is identical to the past, this is a problem that requires generalization. And in general, as a very generic principle, this requires searching for a solution that not only fits, but also is a solution which is simple so that it doesn't overfit and it can generalize well. We could give some take-home concepts, which are that learning extracts a model straight from the data. And the model, what it does is that it blindly optimizes that the loss function or objective function that you have chosen on the data provided. This is intrinsically prone to overfitting and generalization or extrapolation errors. And therefore, you also need a training set and an independent validation data set. So, any question until now? Okay, so we are going to go more in the details about the neural networks. I've mostly skipped the part about perceptrons, multi-layer perceptrons, and so on. So give that a perceptron does a weighted linear sum of numbers and applies a nonlinearity. So the next question is, can we just throw an image at a multi-layer perceptron? So what it does is that linear combination of neuronal values apply a nonlinearity into each individual number, and then again do the same. That's universal, simple. There's an elegant theory that says that this is can generalize a lot. We said it's a universal approximator, and it's super parallel. That's good for computation. It has the downsides are that it has weak inductive biases. What's an inductive bias? That's the kind of your hypothesis. Like, I'm looking for a quadratic relationship. I'm looking for an exponential relationship. Here you're not looking for anything specific at all, because these neurons don't really prefer any structure over the other. Therefore, it's very sample inefficient and data hungry, because even learning a cubic function as a sum of ReLUs, it can be done. That's the universal approximation theorem, but it takes lots and lots of neurons. And dense, which means a fully connected multi-layer perceptron, take a lot of time to compute, or resources. So what you can do, I suppose we get this image here. We have lots of objects, and but large part of this image is just the sky, which is a background. And how do we want to classify this image? Bird, flock of birds, sky. So, and how do we deal with that? We can think about dividing these in patches. And we take each patch, feed that into a classifier, and it says, okay, this one is probably a bird. Then we take the second patch, and it's the sky, and we get to this situation here. And that's what could happen. And we might think about doing that with a multi-layer perceptron. If we have a small patch, like 32 by 32, that's pretty easy to compute. And the question is, what happens if the objects don't fit nearly into these patches, and how we can increase the resolution of the output? If you increase the number of patches, it's not easy to recognize the content in each small patch. So we will use overlapping patches and maybe just try to classify the center of each patch. And we get to the semantic segmentation that we've seen before. The concept behind doing that, if you think about it, is that of translation invariance. You take a patch and a part of the image, and you process it, every patch, in the same way. This is called, in the older computer vision approach, equivariant mapping. So you have a function, and the output of translating the input is equivalent to translating translating the output. So what you're doing, basically you get this your multi-layer perceptron with its own weights, and apply the same weights to every different patches when you're shifting the input. Because you need to remember that this W, if you want, is the weighted sum of all pixels in the patch. What you will do with a fully connected network is take all of the pixels in an image or in a patch and connect them with all the layers in the output. With a locally connected network, to think of, you use the same weights to process every input and its direct neighbors. If you work this way, what you get is that you are getting a convolutional neural network. So in matrix notation, in algebra notation, you get the output, which is a matrix multiplication of all the input. And all of this matrix is, these are all the numbers that you need to learn. So if this is a 1 million pixel image, which is not that much, this is a 1 million times 1 million matrix. However, with a convolution, what you're doing, most of this matrix is empty, and these three numbers that you get along this diagonal, well, most likely it will be 9 more than 3 because you're going over two axes, will be the same repeated. In linear algebra, that's called the Toeplitz matrix, which means that all the numbers are repeated with a pattern. And you could see that as a constrained linear layer. So, and with fewer parameters, which, by the way, that's a kind of euphemism because you're going from 1 million times 1 million, which is 1,000 billion parameters, to 9 parameters. You have something that's much easier to learn and less prone to overfitting. By the way, convolutional layers can be applied to inputs of an arbitrary size, while previously you had inputs that were the number of neurons constrained the number of inputs that you had. And so it generalizes automatically due to its architecture. So you can see convolutional layers, the backbones of convolutional neural networks, in 5 different ways, as something that's equivariant with respect to translation, as something that's processing images one patch at a time, as image filtering, because the convolution is a filter if you analyze images in Fourier space. It can be seen as a way of parameter sharing with a multi-layer perceptron, or also as a way to process variably sized tensor, which is an intrinsic properties of your images. Let's just do a quick recap of a convolutional layer. Suppose that you get a 32 by 32 image by 3 channels, red, green, blue if it's a natural image. You have a 5 by 5 filter. Convolve means sliding over the image, especially computing the dot product. The number of weights in this case, so if you have 3 channels and a 5 by 5 kernel, will be 5 by 5 by 3, so 75 plus 1, because in general we add 1 bias parameter. 76 weights as compared to 3,000 and something for a fully connected layer. If you convolve and slide that over all the spatial locations, you get a 28 by 28 sites output. What you can do is that you can, the output, given that you had 3 inputs, will be, okay, you can add multiple layers, and in general that's what you do when you build the convolutional neural networks. That's an arbitrary number, and so you can get, in this case, maybe we set to have 6 5x5 filters. We get 6 output with activation maps, and we go from a 32 by 32 by 3 to a 28 by 28 by 6. The total number of parameters multiplies by 6. In the middle of that, you just, in general, you put activation functions. You've probably seen that you can change the parameters and add a padding of zeros in the outside to keep the same size if you need that. And what happens if you keep on doing convolutions after convolutions is that when you do the first convolution, it can be shown in the frequency space, in the Fourier space, that these filters, when you use a small kernel, once they use the 5x5 or 7x7, nowadays it's mostly standard to use 3x3, you are basically doing a filter that filters around one specific frequencies with a very simple structure. And so what you get in output are some low-level features, like you see edges or things like that. The more you keep on convolving, the more... so here the output of this convolution is informed by a 3x3 neighborhood or a 5x5. The second layer after the second convolution, every pixel in output is informed by, if you're using 3x3 kernels, is informed by 5x5, and you go on. Every pixel in output is kind of informed by all of the image and not only by its nearest neighbors. So what you can do is keeping on doing convolution until then you apply a very simple classifier in general, like a linearly separable one. Now, this is just to show you what happens when you change the size. When you change, you have seen the stride parameters. You can tell the convolution not to move 1 pixel by 1 pixel, but you can also tell them to move 2 pixels by 2 pixels. The output will be shrinked by a factor 2. And this is used to do downsampling in general. There's the padding issue. You've probably seen that already. And there's also the, in many architectures, the one-by-one convolutions are important. These are used to, in general, to reduce size. This means just mixing all the channels together, but without looking at the spatial relationship. You're just looking at the individual pixel level. The properties of the convolutional layers is that you learn a very small number of parameters compared to a fully connected layer. They preserve the spatial structure. The output of a convolutional layer is still shaped like this input. I said that multiple times, that the passing a translated image to a convolutional layer is almost equivalent to translating the convolution output, while being careful of the boundaries. The, I think, last kind of layer that we will see is that of the pooling layer. So we get, it makes the representation smaller and more manageable. And it operates over activation, each activation map independently. So, like in this case, in the ImageNet architecture, we go from, we downsample by factor, in general, it's always 2. It's not forced to be 2, but in practice, you just do that. It can be done in multiple ways. The most popular one, because it kinds of introduces a bit of nonlinearity, is the max pooling. So it means that you divide the image in blocks that are made of 2 by 2 sides, and you get the highest value in every block. You're not forced to do that way to do downsampling. You could do threaded convolution. You can do average pooling, so you average all of the values in this block, and you could also do interpolation. Not sure which kind of interpolation on a 2x2, but there are multiple ways. So that's the AlexNet. That's the first neural network that was produced for image categorization. That was really revolutionary. At the time, it changed the output of the ImageNet challenge. It used 11 by 11 kernels at the beginning, then going 5 by 5, then 3 by 3. It did some max pooling, convolutions and max pooling, and at the output it went to, you linearize these 13 by 13 images, 13 by 13 pixel images with 256 channels, because the deeper you go, in general, you decrease the number of, you increase the number of channels. Then you say, okay, here, every pixel here is informed by basically all of my input image. So I will just take all of the numbers there, put them in the vectors, and put them in 2 layers of fully connected neural networks, and do a classification in the old way. In this case, it was 1,000 dimensional vector, because it was the probabilities over the 1,000 categories of the ImageNet competition. It had 6 million parameters in total. From then on, we went with the most bizarre ways to invent architectures. You need to remember that given that the universal approximation theorem, every architecture that is deep enough, most likely it will eventually work, given that it's deep enough. So what all of these empiricism around architectures deals mostly with 2 factors. One is how fast you can compute the operations, and the other factor is how well can all the layers be trained. Because whatever architecture, if it has enough parameters, most likely can learn anything, but more often than not, you cannot really propagate the information deep enough. So this is kind of what I said before. When you stack multiple convolutional layers one after the other, you end up with a very big nonlinear convolutional filter. If we take a look at the big picture, CNN can be thought as a function that goes from images to class scores with millions of learnable weights, leading to a very nonlinear mapping from image to features and from features to class scores. We will set the weights based on the classification accuracy and on the training data, and hopefully it will generalize to new images. So the data for that is key. So we have the ImageNet competition, and this ILS VRC image with 100,000 images. The standard metrics are the top 5 errors. And this is probably what I've started my course with. This is what happened when AlexNet was introduced. This was the pre-deep learning era. And from the deep learning era on, we went to a precision that's much, much higher than the human precision, because if I show you the images that were failing these, there was one image which is some spots of red and white, and it turned out that that was supposed to be a pizza, but it was cropped so small and so distorted that even you human don't recognize it. So let's see some practical use cases to finish this in how you can use neural networks. The first use case is the convolutional classifier. Let's say that you have 128 times 128 image. That's a standard architecture. You do like 2 3x3 convolutions with increasing number of channels. Then you go 2x2 downsampling, maybe with the max pool. You are left here with 64 by 64 image. Then you get to 32 by 32. And if you go all the way back from here to here, you see how probably even at this layer, each pixel here is informed by all the 128 inputs in the image. Then you flatten the output, that's the standard term, and you do just a simple classification. How can you use it? As image to categorical output, or image to number if you want to do a regressor. And you can also do image to image. You can do semantic segmentation, instant segmentation, or image denoising. We have defined these two before. This one will be pretty trivial to understand how to build it. And image to number can have many, well, image to category is pretty obvious. Image to number can have multiple applications in medicine. You can like predict a score of some pathology, a neuropsychological score. Like at the moment I'm working with Parkinson dementia, there is a tremor rating. And you can try to predict from MR this tremor rating. And then I've told me that many of you did not see that. Let's take a look at the UNet. You have seen that I've said that the last kind of processing that you can do is an image to image. That's a very generic structure for an image. We can call this an encoder that starts from an image and goes to what we said, it's a very high level of abstraction. If we need an image in output, what we can do is kind of the mirror of what we were doing in this encoder. We start to interpolate to higher spatial resolution and just do some convolution until we get an image in output instead of just converting to a classifier. Now, we have said an infinite number of times that this is a universal approximator, so it should be possible to learn this. Actually, it is possible to learn this. It works in the autoencoder. The autoencoder is and we will do one exercise about that, is a very standard application. However, you will find that training this kind of network is really, really hard, and this piece here, which you might call a bottleneck, needs to be really wide to, even if you just want to reproduce the same image that you have seen in input. So what was a very important discovery that was technical innovation that was introduced in 2017, if I remember correctly, that of a UNet, and that was the introduction of this skip connection. This is a kind of residual network approach, if you want. What it does is that the features learned at this level of spatial resolution are concatenated with these input features here, and so on at every resolution layer. What this means is that you are able, the network is able, therefore, to concatenate some information about the whole image, the whole context, with very local information like the position of contours of some structure. So to define a UNet, you have the number of filters in the first layer, the number of levels, that's wrong, And in general, you double the number of filters that you have in every layer the more you downsample. How can you use that? We have the first approach. The first case is the semantic segmentation. I've represented my UNet here as a black box. You just train this network to go from this image here to get in output these patches that you have seen on the Bratz database notebook. And you can just train the network to predict them. By the way, you have seen in that notebook that we had for each subject 4 images that were aligned, that someone for us aligned pixel by pixel. And we have seen that the diagnosis depends in some way on the comparison between the 4 images. So how can we deal with them so that the network can exploit best all of the information? We can actually just concatenate, as they were red, green, and blue in a natural image, multiple MR sequences. The network will fuse them and learn to do the comparison. Also, we know that the neural networks here are, in general, are in 2D, but our MRs are 3D in this case. So how we can do with them? We can actually do 3D convolution. It takes quite a bit of computational resources, but it's possible to do that. Or either it's possible to process one single slice at a time, or you can just pass the network 2 or 3 neighboring slices as they were different channels. By the way, over time, people invented lots and lots of different UNet variations, but the core, when you need to do an image-to-image translation, is still that of the UNet. Multiple variations, like you have 4 channels, you can fuse the features only at the level of the bottleneck, or just put them at multiple channels, and all of them actually work. Some will be more efficient for your task, some less, but that's it. Now, by the way, there are multiple validated medical devices based on that nowadays that do tasks like organ delineation, lesion segmentation, contour recognition. So it's pretty standardized by now. Another thing that you can do, from which we will do some other experiments in this course, is that of denoising. In the first example, we did image to image, where the output image was a label image. So the output was values like integer values like 0, 1, or 2, or maybe one hot encoded to do the categories. But nothing prevents you to just train a network to go from this noisy image to this noiseless image. You just provide pairs of noisy and non-noisy image. You just train your network to do that. And again, there are multiple validated products about it. You can see here also the zoom in from the denoised image, and it's, I will say that it, well, at least in this case, but of course it was provided by the people who invented the same algorithm, so they choose it well. It goes pretty well. We will do a lab experience where we will see where it fails, and how it fails, and why. And you can also do some domain transfer. We have so this is a paper, this should have been this red circle here. That's already something from 2017. It's not really even that novel anymore. So for some medical applications, you might need a CT. but we have said that CT gives radiation dose to patient. It's one typical case is the radiotherapy planning. You need to know a map of the X-ray attenuation coefficients over all the body, but you're already acquiring an MR because maybe you're dealing with a brain tumor, which you study with MRs, and so you want to spare those to the patient and also spare machine times, and you need a CT. You could just train a neural network to predict the CT given an MR in input. And it's basically also that a solved problem. These are images from 2017. And we can already see some limitations of this approach, because we have said that in MRs, the MR image will intrinsically get the exact same signal from air and from bones, because both of them have no hydrogen nuclei. So here, in this part of the brain, for a neural net, the only thing that a neural network can do, well, not a neural network, any learning system can do, whether it's a neural network or something that hasn't been invented yet, is to learn the average aspect in all humans. The most perfect ideal system. So it says, okay, around here, I see this hole here, I see probably some bone marrow here, let's fill it with bone. But here in the it's called the temporal fossa, we have a very complex structures made of bones and air, and so the average structure in humans is not that well defined, because there's a huge inter-subject variation. So here you will have in general, what you will get, by definition, is the average of what happens in all humans. So you're getting some kind of slightly blurred contours as compared to other regions where the network is much more certain. And you can see even here inside of the nasal cavities that it cannot recognize very well where the bone was. And by the way, here we also have an issue with the training data, a common occurrence. To get these paired examples, what you need to do in practice is acquire the NMR. Then, even if you're super lucky, you just rush the patient out of the MR scanner up to the CT scanner, there's no less than 20 minutes variability. And the nasal cavities often can fill, because if you have an allergy, if you have a cold, they can fill and change their shape and push back some structures around here, change the exact position here. So the data set will not be matched very much, so not perfectly. And that's the head. And the head is the single most rigid part of the body. Like the brain, you can always realign it over multiple sessions. Like in radiotherapy applications, you want to reposition the stomach or everything around here for subsequent irradiation over 1 month. And these are called soft tissues, and they are pretty elastic, so half a centimeter error between one session and the other is very common. And you get air in the intestine, you get the different bladder filling, and so in these cases, the matching can be really, really hard. So we always remember that when dealing with all life science data or sociological data, the ground truth has a huge level of errors that you can reduce. So other applications, you can really get creative. There are some standardized atlases to realign the brain for neuroscience studies. And you want to deform each brain to this reference map. And so you can just ask a neural network to produce this image of elastic deformation map. I'm not sure whether this line of research is still used or not, because alignment is still very important in neuroscience. Even with neural networks are changing a lot the pre-processing of images, but I don't know what's the state of the art for alignment. So last thing is that of data augmentation. We have said that networks and most kind of learning system of very open-ended learning system, if they are open-ended, are intrinsically prone to overfitting. What you might think to do is to create some fake examples and make your data set incredibly infinite. That's not really the case, but what you can actually do is modify artificially the images so that the network learns what not to learn, so irrelevant features. As an example, rotation, translations, for sure they're irrelevant. Realistic levels of noise are irrelevant. Changes in sharpness, intensity, and contrast are all things that can depend on the acquisition camera, depending on your modality, so they should not be learned. Some modality-specific artifact maybe also. And that can be a bit handcrafted. There's really huge lots of, I don't know, you know that, we haven't seen that in this course, but in MR there's an artifact called bias field, which changes it's a very low frequency corruption of the image, change in brightness. And so you can say, okay, I will change that and tell the network that the prediction should be irrelevant to these changes. And this can be very helpful. I mean, it used to be very helpful in general to improve a bit the performance of the network. But it turns out, we will see that in the next lectures, that actually nowadays it's really the fundament of foundation models. You can just tell the network, you have images without labels, and you just say, learn everything about these images and just make sure that images that underwent augmentation are classified the same way, even if you don't have really a classification. That's really, it went from a quick trick to something very fundamental. So some things to remember about that is that, again, universal approximator, and they do exactly and very blindly what you ask them to do. So you need to make sure what you are asking them to do. So the loss function is fundamental, the training procedures and the data set are fundamental. The natural architecture, actually not really that much as you would hope. A very minor consideration about the network architecture that will be helpful for us for our very simple exercises that we will do, that will make us able to run some experiments on our own laptop, is that the main defining feature of a network is the number of trainable parameters, and you want to compare in general the number of parameters to the number of examples. Like if I tell you I have 20 points and can I fit a 30-degree polynomial, you will say no. And how we can do this same kind of intuition for convolutional neural networks? In general, in a fit, you need a number of samples that is greater or equals than the number of parameters divided by the number of dimensions, the dimensionality of the sample, if the samples are independent. In an image, the number of pixels is not really the dimensionality, because pixels are by far not independent. A standard UNet will have between 1 million and 10 million parameters, and a simple MRI after cropping and some resizing will have 10 to the 5 pixels. So actually, the number of samples that you need is, for a neural network with 1 million parameters, is something much greater than something like 10, not something like 1 million, if you want, because each individual image brings really a lot of information. So here, given that they are not independent, here there's not a greater, but a quite greater, but you can, the thing is that you can train a decent network with some 100 samples and work well enough. Of course, the point of, that's useful for exercises, the point of big data philosophy is to have something that will learn very large, very complex spaces. But if you are thinking about, I don't know, can I learn something from 100 patients? Actually, you can learn quite a large number of things. Okay, so that's it about these, all of these excursions on the use of AI for images. On Thursday, for which we already have the room, we will instead mostly do all of finish the previous notebook of the traditional classification, and then start to do some very small tricks with neural network. The other topics of this course will be unsupervised learning and what's that? And we will do a bit of denoising using the tools that and both these topics will be done using the tools for which we've done some these quick refresh by slash overview today. Okay. Any question? Anything about any topic about you think you might need some specific, I don't know, thing to study more in depth? Okay, so we will